We are a facility which is going to go inside of the International Space Station as an express rack payload, and it is a fundamental physics facility which will allow scientists to perform research on something called Bose-Einstein condensates, which is another state of matter where we get down to temperatures which are incredibly cold, meaning 100 times 10 to the minus 12 Kelvin, which is on the order of 1,000,000 times colder than even the temperature of space.
How in the world did we come up with this idea that we needed this?
So it is a science experiment, and condensed matter physics is one of the most important areas of physics under research today, and we're able to create these Bose-Einstein condensates using a technique called laser cooling. And when you use this technique called laser cooling in a microgravity environment, which you get on the space station, you can get to much colder temperatures. And so basically we want to see what happens when we get matter down to these temperatures, because they actually start, instead of behaving like particles or billiard balls, matter actually behaves as waves.
What does this facility look like? You said it goes in an express rack?
Yes, it goes inside of an express rack on the space station, and it's about, I would say, about the size of 2 filing cabinets in width and about a filing cabinet in depth. And it's a box, and inside of the box we have all of our electronics and our lasers and our physics package, which is actually the heart of the instrument. So from the outside, from what the astronauts can see, it looks like a box. From the inside, it's a very sophisticated laser optomechanical system.
Laser optics has become quite a hot topic, a hotbed on space station, right?
I think so, yeah. And so in particular, this will be the first demonstration of laser cooling, which has a whole bunch of technology applications as well.
So not hot, but cold.
Yes, so it's a little bit counterintuitive where you can actually use lasers to cool something down. And what you're actually doing is you're using the momentum of photons to push on atoms which are coming towards it. We are pretty much autonomous in the sense that we're controlled from the ground. The crew will have to install the experiment, and over time there may be parts of the experiment that need to be repaired or upgraded, and the crew will do that as well. So this experiment is designed to be modular, but in terms of nominal operations, it's all operated remotely from JPL, and we specifically operate during the crew's sleep period because our instrument is sensitive to vibrations.
ISS will become the coldest spot in the universe through this experiment. We will also observe over an extended period of time, and we really don't know what to expect. We have some assumptions. So what really makes it interesting about Cal is this element of the unknown, of the discovery, of the future exploration of a region which we don't know what we would expect. And it's interesting to see it started in 1920s with Einstein, and Cal only through ISS will enable us to uncover this unknown. So we were all excited about what Cal and ISS combined will provide us.
So the Cold Atom Lab is just the first step.
That's correct, because we feel what laser has enabled many applications on all aspects of physics and daily lives. What laser did to physics, and you know how lasers are being used, in medicine and so on. We believe that by cooling atoms to this very near absolute zero temperature, will also open up an array of technologies from super computers to many applications in medicine too, and also in transportation.